All right, so we're first going to review kind of all of DeepRL, like I said, in 20 minutes. So this is going to be a crash course. I'm actually hoping most of you are somewhat familiar with this content already, and it's going to be a refresher. So I'll ask lots of questions. If you do know it, feel free to show off that you know. If you don't, and you want to learn this super fast, I put Spinning Up in DeepRL from OpenAI. I think it's actually a pretty good resource, even just a refresher. If you're like, I understand RL, but I forgot what TRPO is, you can kind of check that website. It has some good short summaries. Okay. RL algorithms broadly fall into this taxonomy, which is also from Spinning Up, by the way. There's model-based RL, which I'm not going to cover a lot of in the course, but you're feel free to do that for your projects. And then there's model-free RL, which is what I'm going to focus on. And that broadly falls into two categories, which is on-policy learning, which I'll talk about second, and Q learning, which we already started talking about because we've already talked about Q functions in the last lecture, right? So I'm going to give you like the most basic Q learning algorithm, which is just DQN. That's one of the first DeepRL algorithms. We will talk about some of these other methods in future classes, and I've highlighted at least Hindsight Experience Replay as a cool thing you can check out on your own, because this is like replicates very well and is a very effective method. We're kind of focusing on stuff that works well. So starting with this offline Q learning setting, deep Q learning, if we recall from yesterday or last time, this was that temporal difference error, that neurological signal that we think is so cool. And it's basically that difference between how well you're currently estimating the reward and this reward you actually got plus this bootstrap estimate of the future reward. So we already talked about this. In DQ learning, you just train a network by taking gradients of this loss. So we just set this up as a loss. It's the mean squared error between these two terms and optimize it with a neural network. So this looks like this. You might have some states of your Atari game coming into your neural network, and you're outputting the Q value for this state of all the different actions. Okay, so state comes in, and I say I have a bunch of different actions I can take, and I estimate the Q value for each action. Reminder, this is a recap. What is the Q value of SA? What does that tell you? Yes.
Total rewards that you get after taking action.
Yes, total expected future reward I can get starting in state S, taking action, let's say A1, and then following my policy thereafter. Okay, so this is evolving as your network is training, because your policy starts out kind of dumb, so your Q values might be low, and as it gets smarter, you have to update them, right? Good. So we're going to train these parameters of this network with our previous beautiful loss. Pretty straightforward. So do you think just doing that works? Would I be asking if it did? The answer is no. You actually need a lot of tricks to get it to work. And that was kind of some of the contributions of this original deep Q learning work. A key thing is to use a target Q network for stability. So you're estimating your current Q values with this Q network that you're actually updating, and you're using the target Q network to estimate what you're going to get in the future. Does anyone know why you do that? So this Bellman loss is very high variance and kind of unstable, because you're creating your loss based on your own network. And there's been some cool work, which I'll talk about in a second, that shows that this can cause problems. And so what this is doing is saying, estimate this part with a different network that is going to update more slowly. That makes the loss stay more stable and smooth and not jump around as much, and kind of reduces this problem of training the network to predict its own outputs, which can cause issues. Okay. So there's that. You update this target Q network kind of gradually. So it is interpolating between its own weights in the past and some parameter that nudges it towards the current Q network's weights. Okay. Yes.
Is that updated like how you do it in student-teacher network, like it's mission moving?
Yeah, you can do that. Some implementations that are hackier, which I would not recommend, is like every 10,000 steps, target Q network equals Q network. like just copy, but the exponential moving average of like doing it more slowly is a nice approach. Yeah. Okay. Cool. Does that actually work? What do we think? We're getting a shaking head. Anyone feeling confident? Okay, let's see. So this is the interesting work I wanted to point you guys to. Aviral Kumar is really smart guy. He's doing a lot of interesting work. He has some stuff on fundamentally, it's hard to get neural networks to optimize this Bellman loss. So what he's saying is basically you can look at the rank of the neural network matrix. So kind of like what is the class of functions that it's able to approximate, and it's collapsing over the course of training on this kind of Bellman loss. And we think he has some thoughts in this paper, which you can check out if you want, but it's like making the network predict its own outputs does something that collapses the expressivity of the network. So if you think about it, like DeepRL in some sense hasn't had its like ImageNet or GPT moment. There's many reasons that it's still hard to get it working. Otherwise we'd have, the household robots. So I think this is like one of the key optimization issues that we have with DeepRL. And sounding off a little bit more, like if you think about the deep learning revolution that kicked off with ImageNet, a lot of that was about how do we actually optimize these networks. So like what loss activation functions do we use, loss functions do we use that make them easy to optimize? I think there are still some optimization difficulties with DeepRL. So something to think about. The other thing we do with DeepQ learning is to have this experience replay buffer. And this is actually a concept that occurs with even online algorithms like PPO, so it's good to know. Does anybody remember what these SARS tuples are about? No. Okay. We talked about this last time, but it's basically like for each time step of interacting with the environment, it's like one unit of experience. It's a qualia. You're a philosophy major. So it's like you are in state, you take action, you get reward, you transition to next state. That's like one experience. Put a bunch of those in a buffer. And then to train your Q-learning algorithm, you're going to randomly sample from the buffer, right? And plug those into that Q equation that I mentioned. So if we scroll way back, right, that's where these S, A, R, S, T plus 1 are coming from in this equation. Yes? Okay. Please feel free to speak up. We're moving fast, so you can always review this later too. Another fancy trick you can do is prioritized experience replay. So sampling items in the buffer with the highest TD error. So why might I want to do that? This is good to think about first.
These are like the most informative examples.
Most informative examples, exactly. So think back to our sparse reward learning problem with the baby wiggling around and moving his leg when he's trying to move his arm, right? How often is he actually experiencing a reward of like hearing that bell? Not, right? So you're often, if in a sparse reward problem, a lot of your experiences, like your R, is just 0, 0, 0, 0, 0, 0. Can you learn anything if you didn't see a reward? No, not really. So what you might do is the one time that you actually saw a reward, this is going to give you a real update that you can actually learn from. So you can prioritize sampling based on those experiences that cause the biggest updates, as in have the highest TD error, because those are useful. Yes.
Do you think this is what we're doing when we like have flashbacks to embarrassing memories?
Maybe. I'm not going to speculate that much on the human brain stuff. We can get the neuroscientists in the crowd to say. I don't know. But yeah, so that is a technical thing we do. Any questions so far? Okay. Oh, I mentioned the baby. Yeah, okay. This is cool. If you want to actually think a little bit harder about what training on zero reward forever does to your network, we did a little bit of analysis here, so you can go check this paper. Yeah. Okay, we mentioned exploration was a key problem in RL. Why did we say that it was? Anybody remember? Yes.
It's very large space to look through. It's like going on one person. It takes a lot of computing.
Correct, correct. So it's a very large space you're looking through. You're a baby trying to hit the bell, but you have no idea how to control any of your limbs. So you're just wiggling, right? That's a lot of space to look through to find the arm grab, right? The other point for those of us that are, you know, very LLM forward or like thinking of LLM land, right? There's no pre-training, right? In this random exploration setting. So we don't know what to start with. And so how do we actually find those behaviors? We're starting from scratch. We're generating our own experience on the fly. So how do we do that? It's a fundamental issue. How do I get those highly rewarding experiences into my buffer, right? If you're in LLM land, you're pre-training on all of language, great, you're good. Not so for traditional RL. How do I cover the state space? So there's actually a whole line of work on intrinsic motivation for RL, which are kind of general purpose incentives or rewards you can add or try to optimize that will just help you learn about the problem in general. So for example, curiosity incentives are designed to help you explore. Can anyone guess what I might mean by curiosity, or have you seen something about that before? Yeah.
A reward for achieving a state or action that hasn't previously been seen in your game.
Exactly. So finding some state or action that you've never seen before. So just novelty bonus, right? And that's surprisingly hard to compute in like high dimensional state and action spaces. So there's like a whole literature on this. It's very interesting. I would check out random network distillation or Go Explore for kind of the state of the art in these techniques. These you'll have the slides, so you'll find the links. How could I explore it without a fancy intrinsic motivation? If I don't want to do all that, what do I do? Yes. That's totally valid. Yeah, reduce the action space. Yeah, this is a classic thing. We've been doing a lot of grid worlds in our group, which will have like a big action space involving like pick up or do nothing, and they're not relevant to the problem. If you just take those out, it works better. So
like kind of like using simulations to kind of like limited action space, so that they can only like if it goes out of bounds, it can't.
Yeah, that's good. So in robotics, you can make sure it doesn't go out of bounds, and that makes sense.
Kind of steep.
Yeah. Yeah, a lot of hacks you can do to get this working. That makes sense. What else? Like, yeah. Epsilon greedy, dropping the RL knowledge. Exactly. That is this. Okay, so there's kind of two ways to think about this. Epsilon greedy is you sample a random number between 0 and 1. If that number is less than some epsilon, you act completely at random, just a random action. Otherwise, you take your best action that you've estimated so far, right? So this works pretty well, but what epsilon should I set it to? When should I be acting more randomly, and when should I be acting less randomly? Start of the training is more exploration, right? By the end, I kind of want to do my state-of-the-art thing. So what should I do to epsilon over time? Hi, Neil. Exactly. Time, right? That's epsilon. What is Boltzmann exploration? Oh, I should, I'm going to jump back. So by the way, when I'm doing my beautiful Q network and I have these Q values, what's a good way that I could decide how to act? Think in PyTorch, okay? So I've got this network. It's outputting a final layer of Q values. Now I want to sample an action. What should I do? Yes. Yes. If I take the softmax, this is going to give me what looks like a probability distribution where the probability, I'm going to have higher probability proportional to my Q value. So hot actions that I think are more rewarding have higher probability. So then what I can do is just sample from that. Oh, there was the epsilon decay thing. There you go. So if I just take my softmax and I sample, I'm going to sample with higher probability on the better actions. So this kind of solves your annealing problem. You don't have to anneal manually, because when my network is randomly initialized, what is my Boltzmann distribution over my Q values? Uniform, exactly, completely random, right? So then I'm already exploring randomly. As I learn more about what's rewarding, the entropy in that distribution goes down, and I'm already exploring more towards higher rewarding actions. Yes,
People usually still enable temperature softness.
you could. That's like a thing you could play with and you could try it. I will get into that monitoring the entropy of your learned distribution is actually a good thing to do. And that can be helpful. Yes. Yeah. Other questions? Yes.
So when you then to initialize your neural network,
Mhm.
you do like highly varying result outputs at the end. Rather than-
No, it should usually be like uniform noise. Yeah. Okay. Let's debug a real example. Okay, so I'm gonna give a little bit of a rant. So I strongly encourage you, if you're into this kind of work, go read a Recipe for Training Deep Neural Networks by Andrei Karpathy. It's a blog post. So what it goes into is to be good at deep learning, like empirical deep learning AI research, you need to be like amazing at debugging on steroids. Because if your thing is failing, is it because your research idea is bad or is it because there's a bug in your code? And actually chasing that down is like a very hard problem. And you have to be really good. There's like a really important skill, which is like building better visualizations, thinking very logically, coming up with experiments that would let you exactly assess what is going wrong. And this is key, I think, to success in this type of research. So go read that blog post. It's something to work about. One spiel that I always give, this is maybe why you guys are laughing, is build visualizations early. Visualize early and often. Visualize everything you can. Track every metric, right? So this is like an example of a grid world visualization I built for a multi-agent grid world. It shows the agents running around. It shows what they can see, because if you only are looking at this, you might not realize that you've got some bug in what is getting fed to the agent, right? It shows what action they're taking, what rewards they're getting. This one, this is the cumulative return. So the reward the team is getting over time. So what it's showing is the reward at each step. What do you notice that's different between these two movies? What's going on in this one on the right versus the one on the left? Graphs are different. Graphs go up. I like when graphs go up. What's happening here? Not. So something's wrong with the one on the left, right? So we need to debug why. So this is a large, partially observed grid world. So the agents are only seeing part of it with sparse rewards. You only get a reward if you go to this green goal, okay? So let's figure out what's going on. Oh, I don't want to give it away. RL can be very sensitive to hyperparameters. And this can be, there's sort of an art to exploring this space and getting it to work. So especially in sparse reward settings. What we're going to do is we're going to guess which hyperparameters led to which curve. So this is what they pay me the big bucks to do, is just stare at learning curves and tell you what happened. So they don't actually pay me the big bucks that you all right, so what do you think Ep's decay is? Decaying epsilon, but why 500,000? Training steps. It's going to decay over the training steps. So we here have 4 million training steps, okay? So 500,000 is going to be like right here. Okay, so hyperparameters A is decaying epsilon to what value? Ep's end, good clue, okay? So we're reading the code, it's not documented, we're just reading the names, we're figuring it out. What do you think buffer size is? Replay buffer size. Okay, so this replay buffer is 1 million. What do you think happens when you fill up your replay buffer to the limit?
It's a FIFO queue.
It's a FIFO queue, so first in, first out. So what's going to happen is, what happens to my oldest experiences that I've had? Out. Okay. So now what this is saying is the exploration is decaying. Sorry, where's my 1 million? By here. And then after 1 million steps, I start replacing any experiences I had. We got it. Oh, good clue, good clue. All right. In contrast, okay, hyperparameters B decays the epsilon over 4 million steps. So the whole training run, okay? The epsilon end is smaller. So what's the implication of that? Anybody know? Yeah.
Takes longer, but then at the end, it's more deterministic.
Takes longer, but at the end, it's more deterministic. Exactly. So this is like a small constant rate of exploration This is going from a lot of exploration for a long time, but eventually like very deterministic. Okay, good. And buffer size 20 million. So are we ever replacing experience? No. Okay. Similar, epsilon decay here is 1 million. So it's exploring until here, right? And then epsilon end is higher, and buffer size is 20 million. So we're not replacing. Okay, so with all of that in mind, what's going on with these curves? So blue, what's happening with blue? Not learning, failing to learn. Okay, what's happening with green? It's learning, but is it a little slow? It's taking longer. You're taking more samples. Okay, what's happening with red? We like red. It's good. Curve go up. That's our whole job.
Paint, the other thing.
Ah, yes, great question. Why is there kind of faded out stuff? High variance. Okay, so we always plot this, right? So the returns are, this is 4 million steps. There's many episodes happening. Some episodes you win, some you lose. Some you find the goal, some you don't. So it's very high variance. The real signal, by the way, what this is a smooth curve plotting the variance behind it. If you literally plotted this signal raw, it looks like this. Literally uninterpretable. So you have to smooth and then average and show the variance, okay?
Do you just usually go running? Maybe
Yeah, it's like a window averaging. That's just your basic. Panda's rolling average would get you that. Or probably all you guys are just using weights and biases and not understanding how the flux made. Sorry. But yeah. Okay. Okay. So so we said this is good. This is soda converge. This is good. So what do we think? Which one is which?
it's blue.
B is blue. Okay, why do you think B is blue?
I don't know. You have a really large buffer size, so you're not running that quickly, and you also have a very low epsilon and you decay very slowly. So I don't know.
Okay, that makes sense. So you're thinking like it's acting randomly for so long that it doesn't seem like it's learning. The buffer size thing, we still only sample valid examples from the buffer. So the fact that it's so large means like we still keep track of actually we've only filled it up to 4 million and we only sample those 4 million. And so it just means we're not replacing things. But any other guesses? Yes.
C is blue, B is red, A is green.
So you said B is the best group? Okay, so we got some difference of opinion.
Wait, no, C is the.
C is the best one, okay,
B
and
is
B is green,
and A is.
and A is blue. Okay, I'm liking that. Can you justify your choice though?
I think with A, that's not the thing, it's too quick, so it never gets to a policy that's good. And it just fixes on that policy.
So that's actually the correct explanation. So if you stop exploring so early into training, a lot of these algorithms aren't seeing some real progress right here. So you basically have no rewarding experiences in your buffer, and then you can't learn. Right? So if you decay too quickly, you're not exploring enough, you don't discover the highly rewarding experience, you can't learn. Okay? And then what was your justification for which one of these was which? So
B is green
okay.
and C is red. So for B, it's decayed epsilon quickly, so it's exploring a lot. So slower.
Seems reasonable, right? So it's decaying the epsilon a lot, and therefore it's exploring too long, so it's slower to converge. I like that. Does anyone have any other thoughts? Okay, we're going to see in a second. By the way, I made this deliberately confusing. So I didn't do apples to apples. Like if we really wanted to understand what was going on and we were designing our hyperparameter sweep more intelligently, we would keep everything fixed but one parameter and just see how that affects things. But often before the deadline, we're just trying a random sample of things. We're like, what's going to work? And we end up with this and we're like, well, multiple things have changed. How does that explain what happened? So I did that on purpose. Okay, so you had the right answer exactly. So we have a Goldilocks situation. So A does not explore, can't find the great experiences, never learns. B explores for too long, takes it a long time to converge on the correct behavior. C is our Goldilocks. We like those settings. Curve go up. Any questions? Yes.
I know this is kind of like maybe like figure out since sample plot, but like,
Mhm.
does it matter by or between B and C, like the bucket size? We decrease it, would we see more of like lures or?
Yeah, if you if you have such a small buffer that you have a rewarding experience come in briefly and then it goes out, you're not going to get that chance to learn from it. So you can remedy that by basically like keeping good experiences in your buffer long enough to do the sample complex thing of learning from them, right? You can fix that with a larger buffer or prioritize experience replay. So you also like throw out examples that have lower TD error. Just keep the good ones or something.
Would it cause it to learn slower or would it cause it to miss out?
It's kind of complicated, right? Because it depends on luck of the draw. It depends on exactly what your sample size was. Like if you have sufficient, like let's say even for A, from like monkeys on a typewriter, perhaps if I ran this for infinite time, I would still happen to sample a highly rewarding experience that stayed in the buffer for 1,000,000 steps and I started to learn or something like that. So maybe it could still work with enough compute. I'm not very optimistic of like doing that empirically, right? But yeah, it's messy. I don't know if that answers your question. Yeah.
I guess not easily. Why wouldn't you have buffer size infinity?
Well, you don't have memory. What if you're training an LLM? Right. So then GPU memory becomes very high commodity. Yes.
Is the weighted epsilon decays typically better?
I don't usually mess with that, but you could. There's a very high dimensional space of things you could play with and explore here. It's very hard to explore on your own, especially if you don't have that much experience. The best advice I can give you is take an existing implementation and start with their hyperparameters. And then build a lot of visualizations to see if it's working and what's going wrong. Yeah. Okay. I'm going to keep moving because I want to actually get to the RLHF stuff. So there's a trade-off. So once I've started to get some reward, should I stop exploring and just exploit that strategy? This one should have exploited more. This one should have explored more. This one is the Goldilocks. But unfortunately, you don't know which regime you're in if you're underexploiting or overexploiting because you don't know the optimal policy. So that's why this is hard. Okay. I'm going to keep moving. Policy gradients. So this is this side of this tree. Policy gradients are basically on policy learning, where you take your empirical return of the trajectory, which we talked about before. So this is kind of your actual rewards you observed in a trajectory. And you do something really simple, which is you just take the gradient of the probability that your policy is assigning to that action in that state and multiply by basically a score. How good was it? So if this is good, probability go up. If this is bad, probability go down. So you're like assuming you normalize the reward. So essentially, you're up weighting those things that happen to work empirically and down weighting those things that didn't work. And so what this does, so this is your gradient, this is your learning rate. You just do a learning rate on this gradient here. It pushes up the probability of highly rewarding actions, pushes down the probability of low reward actions. And this is the reason it's called on policy or online is if you look into the theory behind this, this is only guaranteed to work if the experience you're generating, like the SA tuples that you're trading on, were generated by your own policy. So in Q-learning, it's called off-policy learning. You can give me any data set of data, and I can try to learn from it, although fully offline learning is actually its own thing and it's hard. With online learning, this experience has to be generated pretty recently from the policy that you're trying to train. Okay. So this is what it looks like. I recommend checking out this blog. Another Andre Karpathy classic is Pong from Pixels. It's very intuitive, fun blog that helps you learn it. I'm going to gloss over this little just because we're running out of time. The problem is this empirical return of trajectories can be very high variance and also depends and is different on each environment. So we can use a smarter score function instead of R, which is the advantage. The advantage is the reward that I got for taking a particular action from state S minus the value function, which is the average reward that I might get in state S. So this is kind of this advantage of taking a particular action. Yeah. How do we estimate this? Now it gets a little harder. We basically need to train more networks, but do we actually have to train 2 more networks to estimate both Q and V? The answer is no, because I can rewrite this equation using the definition of Q to be this empirical reward plus discounted V at the next state minus V at the current state. So I just need to train this additional critic network that estimates the value function. So you'll see this a lot of, on policy gradients methods are training both the policy and this critic. For LLM stuff, this has gone a little bit by the wayside. They do more like empirical estimates of the value using things like GRPO. And then why do you think that is for LLMs? Oh, by the way, usually having completely separate networks to estimate your policy and your critic performs better. So here I'm showing like one network with different heads. Usually you have like a completely separate critic network. So why might that be hard with LLMs? Memory. Having a whole other LLM pricey in terms of GPU memory. We need GPU memory. So yeah. Okay, I'm blazing. Let's keep going. So TRPO is basically a fancier on-policy gradient algorithm. Policy gradients are slowly updating the network parameters. However, a small update in parameter space can actually lead to huge changes in policy space. So suddenly one action early in the trajectory becomes weighted higher than another, and it throws off the entire rest of the trajectory, right? Like walking off a cliff or something like that. So what if we want to do more slow updates in the policy space, in the actual probability distribution that we're outputting? So what that looks like is we're going to optimize the reward while keeping the KL divergence between our policy at, iteration K. Here's my parameters at an iteration. So whatever I'd learned so far. And my parameters after updating them, we're going to minimize the KL divergence between those two things. We're keeping it that within what's called a trust region. That's why this is called trust region policy optimization. So what that looks like in theory is this. We look at how much better is the new policy, but we keep the difference in policy space constrained within this trust region. Now, this type of constrained optimization, beautiful in theory, really hard to do in practice. So TRPO is not what you'll see used in practice these days. Anybody know what you actually see? PPO. PPO is like, cool math, difficult to deal with in practice. PPO is like the workhorse of modern deep RL, I would argue. It's motivated by the same idea as TRPO, doing slow updates in policy space, but you implement it with a clipped surrogate objective that doesn't involve actually computing the KL divergence. And that's easier to do in practice. So you do look at this ratio of the new policy to the previous policy, and you clip that. This is like the state-of-the-art deep RL algorithm. So it's used for RLHF. It's used in OpenAI's whole post-training pipeline for LLMs. It's actually the state-of-the-art multi-agent algorithm, which I'll get to. And it works well in robotics. I've also seen papers that show it's more robust to the choice of hyperparameters. So even if you mess it up, it kind of still works, unlike some other RL algorithms. So this paper, I think, showed you can like squeeze out better performance if you're an expert from soft act or critic, but PPO is better for noobs who don't know how to do it. So just probably PPO is a good choice if you don't know what to do. All right, so recap, we talked about off policy and on policy methods. Off policy can learn from data collected with any policy. It can also be used for offline RL, learning from a static data set that the policy didn't collect. I'll talk more about that. On policy, you must collect the data with the policy you're training, and you can't even use data that's too outdated. So your replay buffer is now quite small, and it's only recent experiences. So it may require more samples, but I've converted to on policy land. I think it tends to work better. But that doesn't always mean more compute. So if you make something super efficient for training, you can actually sample billions of time steps in a small amount of time on a single GPU, depending on how efficient you are. Okay, I'm gonna keep going pretty fast because I do want to get to this other stuff. All right, so what do I do if I'm, you know, in this realm of I'm not learning? My reward curve looks like this. Any ideas? I already clicked one in, so you've got it for me. We talked about exploring more, right? What else can I try to do? Yeah.
You mentioned intrinsic motivation.
That's a good one. Yeah, I could add some extra reward shaping or incentives or intrinsic motivation to try to explore the problem better. Dense reward, exactly. Yeah, densify my reward. That's good. Learn slower. How, like explore more, or what do you mean?
Like small.
Oh, smaller learning rate. That could be true. Yes, that could be true. So if you can have a thing where you over update on it on some experience and your learning rate was so high that you kind of jumped out of a valid region of parameter space and now your thing is messed up. You can't learn. That's a good point. Add a reward shaping term, prioritize experience replay, fancy intrinsic motivation. Talked about those. Yes. Ooh, social intrinsic motivation could be a good course project. We'll talk about that. What if my agent still isn't learning? Oh yeah, I do link this. Definitely read this. Visualize, 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 inspect, figure out what's going on. Make a video of it. Yes. Does this video do anything cool or not? I think it's just that it's not learning. Oh, I know what it is. What you can see here is this agent has learned to drop, 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 drop. Every single action they take, every time step is drop. Drop that doesn't even do anything in this environment. So why is that happening? Any guesses?
Probably forgot to take the gradient.
Okay, so I just like have a complete bug. I'm not even training my network. Very good answer, actually. Yes. Anything else? We actually talked about carefully monitoring something as we were training. We were talking about Boltzmann sampling. Yes. Okay, exactly. Agents take the same action over again. So another thing to do is check your entropy. So as a recap, this is a high entropy uniform distribution. This is a low entropy distribution. If my agent has somehow updated its parameters such that it's collapsed on thinking one action is really good, but that action really isn't good, like drop, 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 then I kind of can't escape from that, right? If the agent is never going to sample non-drop and drop doesn't pay off, your training has bottomed out. It's not going to work. So this is something you can monitor to see, like, yeah. Oh, I should say, I don't know if I have this in the slides. Sometimes training for 10 times as long just suddenly works. So, but should I keep training 10 times longer or should I stop? This is a good diagnostic to know which of those realms you're in. Okay. Entropy can decrease over training, even if your reward isn't maximized. This prevents you from finding rewarding experiences. Real errors I've seen that have caused this. Update every x steps equals 4. What do you think that means? Any guesses what that hyperparameter is doing? Okay, it could be target network. That's a good guess. In this case, it was actually update your policy, like do your RL step. What do you think this means? Why is this a bug?
Like ignore 3 out of 4 of its training steps.
Okay, ignore 3 out of 4 of its training steps. Okay, that could make sense. That could make sense. What this is actually doing is it when you update, assume you correctly sample what's in your buffer. But if you've only done 4 steps, there's not a lot of information about what's going to pay off in your buffer. And then you're actually, this is updating super, super, super frequently. In robotics, this actually might be a good hyperparameter. But if you're in a super sparse reward environment that you only get a payoff after 200 steps, what this does is many, many, many gradient updates, pushing your parameters in some weird direction that's not related to successfully completing the task because you've never successfully completed the task. And so this can cause an early collapse of your policy to a low entropy state that it's not possible to explore from. And so this is a real bug because if you just take some robotics RL code and try to use it, it might have this parameter. It doesn't work. Same with doing 50 updates on every batch. So I have a limited amount of data. I update too heavily on it, pushes me into some weird part of the space that doesn't work. So if we remember our classic ML optimization landscape, right? If I'm trying to follow my gradients, right, that depends on the data that I have, right? So if I have the whole data set, this is like the true bottom of my optimization landscape. But if I have limited data, then my gradients are quite noisy. I might not see this. If I update very heavily on that bad data, I kind of go off into space. And it can become difficult to recover from that point. So it's a lot of these things are quite different from supervised learning if you've done a lot of supervised learning because you're generating your own data on the fly, right? Supervised learning has the data set. It has this. RL is like crafting the data on the way. So it's sometimes like pointing in the wrong direction. So you don't want to update too hard before you've collected better data. Does that make sense? Okay. So we talked about visualizing your policy, check for silly bugs. Yes, yes, yes. Check your inputs are correct, hyperparameter tune. I did put this in. Yeah, sometimes running for 10x the time just works. It's good. If all else fails, normalize the reward to be between 0 and 1. Sometimes that actually makes a difference between it failing and working. And I gave a little bit of a technical explanation of why that's a thing. Okay, that is it for this part of the lecture. Questions? So that was a very huge crash course on sort of empirical deep RL. It is a skill you can develop over time with practice. This is just meant to be get you started on how to get things working, but there's definitely more to learn. Has anybody had experience with this kind of stuff before? Good. Okay, good. Excellent. So yeah, this is a skill to develop more, but this is my best tips for that. All right, let's go to the next part. All right, we're jumping into LLM stuff. Who here has done work? Okay, we already said everybody's using LLMs to write their homework. How many people have done a researchy project with an LLM? Cool. How many people would self-identify as in NLP? Okay, good chunk. Okay, so I moved, like I said, I moved this earlier so we could talk about this because I think it's a lot of interest. So we're talking about post-training of LLMs and kind of how that came about and an intro to RLHF. So we all know we're in this like crazy AI, AGI era. And as we talked about, the key differentiator between ChatGPT and previous GPTs was this application of RL. So arguably RL has been a huge component of the current AI boom. Obviously, you couldn't have this boom without massive scale supervised pre-training and transformers and, you know, systems engineering, distributed systems. Like there's a lot of components, but RL has definitely been key as well. So why do we need RL post-training? Give me some answers. What do we think? Yes.
Make our models more robust.
Make our models more robust. What do you mean by robust?
You can handle inputs that are directed out of different.
Ah, yes. Oh, that's good. I actually didn't put this. Yes. But correcting the sort of like teacher forcing extrapolation error thing. Yeah, that's a really, really good point. So because you're sampling from your own model and then testing how well that turns out, you can correct this error that if you sample something weird that you haven't seen during training, it's now out of distribution and it can break your model. Nice. What else? Yeah.
You don't have to like specifically tell the model how to do something, like let it figure it out how to optimize.
Yeah, exactly. Like it can explore multiple behaviors to find a solution. So this would be true in something like what's a good
Like RLVR, I think.
RLVR, like reasoning tasks, right? How do I solve math problems, even if it's not in the data? Yes. What else? Yes.
Stronger suits the physics test.
Yes, correct. Get stronger on a specific task where you have some metric you're trying to optimize. So again, like RLVR, you could also do like thinking broadly, like patient care or something. Like you want to recommend the right course of treatment, and then you see if that paid off over time or something like that. Yeah. Yes.
Like alignment training.
Mm-hmm.
It's not telling like the whole area stuff, like a real useful system.
Exactly. Yes. So if you just train on all the text, it's not making you a useful assistant. So we actually want to make it follow instructions, be helpful. We also want to make it not say inappropriate stuff. Yes. I think that covered a lot of what I was going to say. So aligning models to make them safer and less biased, make it chatty, right? Learn skills beyond what's in the data. I think you said that. And of course, makes them cache. It's a big game right now. Okay. We know these LLMs are biased. We know they can generate false outputs and hallucinate. Currently, RL post-training is kind of the only thing standing between this level of bias and us. So, you know, there's just a ton of work that language models inherit biases from the data they're trained on. We have some work showing they inherit moral and political bias. So RLHF is really the only way that we can prevent that so far. Why are models biased and untruthful? And let's talk about hallucination as well.
They're trained on a task that's not being unbiased.
That's right. So the fundamental, you kind of got to what I was going to say. Supervised learning, I would argue, is fundamentally the wrong objective for making models be truthful and unbiased. They are just trained to predict the next word or token. And so that is training them to produce plausible sounding text that looks like the data distribution. So there's no incentive to be truthful or non-toxic. If there's, you know, you can just, that's why you get this like confidently incorrect, you know, making up phone numbers, making up facts that don't exist. It just has to look like a plausible completion, right? Yes. Do you have a question?
Oh yeah. Trying to formulate my thoughts. I think a large part, even though there is no incentive to be, well, explicit incentive for non-toxic, it seems to be what some literature say there's an implicit regularization, which is like actually covering a large part of why models are. Well, a lot of times biased.
Yeah. So like if you ask it, you know, who was the 5th president of the United States, there is a correct answer, and most text in the data will say that answer. So then there is that regularization towards the truth if it has high support in the data. But if you ask it, what's your middle name, there is no such ground truth, or there's many possible correct answers. So then the best thing is to just say the most likely middle name, right? It doesn't have to be a true statement. So yeah, but it's good to understand that nuance. All right. So how do you actually increase alignment, train on human feedback? So we talked about this already, about why we need RL. We said there's no way to understand whether something is appropriate or not without understanding the whole sequence. Now you are breaking your gradients, so you can't train with supervised learning, so you need reinforcement learning. We talked about how this is the right tool because it's this sequential decision-making algorithm for optimizing behavior over a sequence of time steps. So when you're doing RL on human feedback for language, the paradigm you use is you first pre-train on all the books and all the internet, and then you post-train or you keep training with RL. Why do you need to do this? This is kind of an obvious point, but I think it's worth belaboring a little bit. Could I learn what sentences humans like from scratch? Let's just play that out for a second. What 3-word sentence do humans like the most? Let's say my vocab is 10,000. What is the complexity of exploring all possible 3-word sentences in a 10,000 word vocab? A lot. Yeah, that was the gesture I got in the back. It's actually 1 trillion. Do you think I have the cash or the time to pay humans to vote on 1 trillion 3-word sentences? No. So you can't afford to pay humans to give you 1 trillion ratings. So if you use a pre-trained model, it's restricting your search space to valid, probable English sentences. So then you might be able to search, let's say, I'm making that number up, but in the millions of sentences, right? This is actually a really important point. So the cool thing that LLMs have changed for RL, and this applies to robotic setting as well, is they're really solving exploration in a really meaningful way, right? A lot of how we've thought about RL in big landmark things like AlphaGo, Atari, whatever, is exploring from random movements, from scratch. That's a crazy hard exploration problem. If you're now exploring on top of a language model that's already pretty smart, your exploration got so much better. So it's a really interesting thing to think about. RL post-training on top of a model that's already good has a very good exploration built into it already. So that's kind of a key thing that distinguishes post-training from RL from scratch. All right. Okay, so today we're going to go into the history of whatever led to ChatGPT. And of course, I have to start with my own work because I was doing this before it was cool. So it's a big part of how I have to get in there. But myself, as a 2016 intern, I was working at Google Brain, and my project was supposed to be doing music generation with LSTMs. Now, how many people have ever trained an LSTM? Nice. Okay, they're still existing. So maybe the roboticists in the crowd. Have you ever trained an LSTM on text or music? Good for you. Okay, nice. Did it work well? At the time. It was the state of the art at some time. Great. So if you train an LSTM on music, we had actually all the Google Play music data. So we had a big data set. But if you train it on music, this is what it actually sounds like. Let me make sure we're gonna be able to hear. Oh, you guys can't hear that. Well, how do I make noises? Podium mic. I'm just gonna do this. So a bit awkward, right? It's like sort of musical, but there's this weird pause in the middle, right? Like what is going on with that? Oh, hold on. So what you're seeing is that it kind of like lacks structure. So this would have been true for text as well. Here's some text generated with an LSTM. Mildly older than old half-sister? What? Like it's sort of plausible, the grammar is there, but the content is not. It's like really lacking this structure that we would say makes sense. So the idea that we had for this internship project was, what if you could use RL to enforce the rules of music theory? So basically ask me to like code up what it means to be good music in some Python, and then compute some score and train the model to optimize for that. I don't really know how to do that. You know, I quit piano after 10 years and never touched it again because my parents made me do it. Classic story, right? But my colleague gave me this book and I was like, I'm going to write up a reward function that is basically coding this up. And I liked it because the first rule was avoid excessive repeated notes, which is a failure mode of LSTMs when they suck. So I was like, yes, this is justifying, you know, from the literature that I can do this. So I wrote this up. We're going to pre-train on data. We're going to keep training with RL. So we're going to learn something about music from the data and then learn the rules of music theory, impose some structure, and fix it. We talked about that already. In this time, some folks were exploring this idea. This is post-training idea. Pre-training on the data and keep training with RL, maybe for translation, like improve translations by rewarding BLEU score. The problem is, if you do this naively, it doesn't work that well. So the reason is, at the time we thought about it as catastrophic forgetting, but you can think of it as the fact that what RL is trying to do is exploit the reward that you're giving it. It's just an optimization tool. It's just optimizing the reward. If your reward function is limited because you're coding up this like rules of music theory, not repeat notes thing, or you have limited data, so you're learning from human feedback, then it's going to do something pretty dumb. And it has no incentive not to just erase what it previously learned from the data to exploit that reward. So if you, for example, train a language model on a reward for asking questions, which you might think that would be a good thing to do, this is what it looks. If you train it on the music theory reward that I coded up, guess what is the optimal composition? Silence, good guess. Actually, infinitely repeated middle C. So, dang. Okay, So how do you fine tune a sequence model with RL? The idea that I came up with at the time was not only pre-train on data and keep training with RL, but keep around a fixed copy of your data model. I'm going to call that a data prior. Now we call it like a reference policy. And you constrain your RL updates to make sure that you don't diverge too much from that data prior. And so this ends up in math looking like KL control from this pre-trained model. So instead of just maximizing your reward, which we would normally do in RL, you minimize the KL divergence between your RL policy and your pre-trained prior model. And so we did this for Q-learning at the time. In Q-learning, it looks like basically just subtracting the probability on your RL policy, which is like doing entropy regularization, and adding the probability under your prior for the individual tokens. We did some fancy math. There was people working on KL control at the time. So we adopted some of those techniques. But at the time, KL control was used more like in PPO or TRPO to restrict divergence from your own prior policy, or to restrict divergence from like a uniform distribution to do entropy regularization. So the key idea here was actually to have this pre-trained prior to do your KL control. And so how that works is if you don't do that, your RL, in terms of the KL divergence from your prior, ends up looking like the actions are totally random with respect to the prior. So it's basically retaining nothing of the prior that it's initialized with. If you do that, it retains some information about the prior. This type of KL divergence from the prior curve is now used frequently when we're doing RL post-training to kind of understand how that training is going. So I'm going to do this again. We heard what it sounds like if you don't do KL control. If you do KL control and those music theory rewards, this is what it now sounds like. Kind of catchy, right? We had some press come out at the time that basically called it like a toothpaste jingle, which is fair, but yeah, I don't know if like the music itself was kind of the greatest scientific achievement, but what we did show is that useful techniques. So we were able to do this for drug discovery, which I will kind of gloss over because we don't have a lot of time. But why you would want to do something like RL post-training for drug discovery is you just sample candidate drugs from a generative model. They don't have the properties you want. They might not be synthetically accessible. But you can use RL to optimize for those properties. And if you do the KL control, you still retain likeness to the data. Whereas if you just do RL, it exploits something silly. So this actually got picked up by industry, was like the predominant drug discovery technique for a while. But the key idea here is to compare just doing this naive fine tuning with actually doing this constraining your updates to stay close to the data prior. We then applied that technique to actually learn from humans in dialogue. So I think our work was actually the first to put a language model online, have it talk to people, and try to use RL to learn from that human feedback. We, instead of doing something like manual labels, took a different approach. So I was very into this idea of social feedback because I think it's more ubiquitous and natural. You get it for free. So what we did was we built this system. You can take your this is now 2018, 2019, fancier LSTMs. You can see they're not that smart, right? So the user says, hey, what's up? And the model says, hi, sorry to hear. A little more grammatical, but not good. And so our idea was we could detect when the user says that doesn't make sense, that they're not really enjoying the conversation at that point, and use that as a signal to train the model. Our hypothesis was that that's going to work better than having the user give manual feedback. So like upvoting and downloading responses. And the reason is that to give that manual feedback, you have to deviate from your chat, right? I have to go to an extra mouse clicking effort to be able to provide that. I'm not really going to do that as frequently, but the signals that you get from the text itself are occurring on every turn. So that was the key idea here. We developed a set of conversation rewards. I'm going to gloss through this based on human literature, based on the past literature. So these are kind of the implicit signals like about the sentiment, And then we built this system to actually interact with people and learn from them. I'm gonna gloss over a lot of the offline RL stuff. If you're curious, we can talk in office hours, but essentially this same thing, this KL control thing works as a really good offline RL technique. I don't have time to get into that today, but here's the key idea. If you don't do KL control and you do RL fine tuning of a language model on these kind of implicit signals, which include asking questions, the model will start saying things like, where did you get? How do you work for you? You want to talk to you about you? Losing its ability to speak English, right? It's trivially optimizing the rewards you gave it at the cost of being a good language model, which is still a problem today, by the way. If you over-optimize on rewards, if you over-optimize on safety of rewards, if you over-optimize on RLVR, you get a worse language model. You have to maintain proximity to the data. If you do that and you train on these rewards, at least in our case, because it was maximizing like positive sentiment in the user, start saying things like, hey, I hope you have a great day and I wish you the best, right? So it's realistic, good, but I think these sentiment-based rewards actually made it a little too cheerful, polite, supportive, became a little too Canadian, if you will. So the KL control thing turns out to be pretty important. If you benchmark doing KL control versus not, it's big, significant differences. That is actually still used in a bunch of RL post-training pipelines today. And so it's used in the sequence of work from OpenAI. I gave a talk to OpenAI early in before they did this work, and then they adopted it. And then it's still using Google, DeepSeek, DPO, blah, blah, blah. But the implicit rewards stuff did not survive. So no one's doing that anymore. I still think it's cool if you can actually show that training on these types of implicit cues do work better than training on manual upvotes, downvotes. But no one is doing that stuff anymore. I think part of it is that, you know, in this work at least, we weren't able to show that optimizing those implicit rewards actually improved the quality scores over the original baseline. So in some sense, kind of a negative result. So we were like, is this like an alignment tax? Like you make it nicer, but that's not actually more fun to talk to? Or do we have the wrong rewards? Or do we just not have enough data? I also think it was using offline RL. So offline RL is actually really, really hard to get working. Online, and so we're using like a Q learning based approach here. Online RL lets you use like something like PPO. So what we did was we set up kind of a self-play thing where we had all those same rewards computed by another LLM answering. And then we compute like, did you elicit positive sentiment from an LLM simulating the human user? So kind of a self-play approach. And then we use PPO and online RL. And it turns out that that works really well. So I think these kinds of like implicit cues-based rewards could actually work, and I'm really excited about it. But I think the technique we were using of doing this offline approach doesn't work. So having gone through this, by the way, we're going to read DPO next week. DPO is an offline approach to RLHF. I'm not a big believer because I just think the offline approaches don't work as well. I think the online learning makes more sense. So yeah. And so we showed, you can significantly reduce the toxicity of your model by training on that as a reward, this kind of thing. Okay, good. I'm actually on about the right time I want to be. So now I want to talk about the history of work coming out of OpenAI that eventually led to ChatGPT. So the first paper we want to talk about is this Deep RL from Human Preferences. And this was about training with human feedback, but not training a language model. So what kind of feedback should we use to be able to actually learn from humans? This paper had some really nice ideas about this. So RL models are very sample hungry, but human feedback is really expensive. Paying a human to come in and give me a bunch of samples doesn't work. So what could I do instead? You may already be familiar with this work, but yeah. So instead of so offline RL would say, every single piece of human feedback, I'm going to put it into a buffer. This is going to be my human feedback, right? And I'm going to put it into an offline buffer and try to learn offline from that data. That means inherently the number of samples that I'm learning on are the number of human data points I collected. This would be true of DPO as well. What if I want to have more than that? I want more RL samples than I have human feedback. Huh? Huh? What is this?
You could bootstrap it, so the training one model will be used.
Yes, that's where I was going with this. Yes. Okay. So you train a human simulator, human feedback simulator reward model that says, given some input, what do I think the human would say about it? And you can train that with supervised learning. It's just predicting what the human would say. Do they like it or not? Then you can use that reward predictor in your loop with your RL algorithm and train and train and train and train as long as you want, because you can sample infinitely from your reward model. Now, your reward model is not going to be perfect. It's only an approximation of what the human would say, but it overcomes this issue that learning to predict what the human would say is an easier problem and takes fewer samples than doing all the bootstrapping you need to train RL. Because in RL, you're trying to predict everything that will unfold over the future. You're trying to correct this out of distribution error, all of this stuff. Yes.
Do you additionally also train the RL human feedback with this the algorithm RL on the internet?
It only interacts with your reward model. Yeah. Any other questions about that? Okay. Why do we expect the reward model to make better use of the data? I think supervised learning is fundamentally easier than RL, right? Just the optimization we can do for supervised learning currently works better than what we can do with RL. The other thing is that supervised learning, you just mimic a data set. You don't have to learn to predict what's going to unfold several time steps from now. So that sample complexity of RL is much higher. All right, I'm going to gloss over this. The other thing that came out of this Deep RL from Human Preferences paper is humans are actually pretty bad at giving absolute ratings, like saying this is a 10 and this is an 8. We're not very good at this. And so they actually looked back at the behavioral economics literature and came up with a better way to get human feedback. What's easier for humans to do versus giving absolute ratings? What can we do? Yes. Ranking, exactly. So we can say which of two things is better. And so that was the insight that they had. So they asked the humans to rate which of two trajectory segments they prefer, because humans are better at making comparisons. And then they said that the human preferences are generated by this reward function, which is this R, such that the sum of the rewards of this must be better than the sum of the rewards of this. So basically, if I'm saying this trajectory is better than this trajectory, that means I think this trajectory has higher cumulative reward, but under what reward function? So this is this BTL preference model. So what this is saying is that the probability that I prefer some trajectory segment to another one is going to increase exponentially with the sum of the rewards of that trajectory normalized against the sum of the rewards of both. So the greater the magnitude and the difference of the reward between the two trajectory, the more I prefer it. And this is noisy, right? It's kind of like a softmax idea. So it encounters like some level of error, but yeah, this is basically the assumption. So, and the human is going to prefer, trajectory 1 if this mu is 1, 0, or 0.5, 0.5 if they're equal. And so you maximize this. This has a lot of connections to inverse reinforcement learning, maximum entropy inverse reinforcement learning, which we'll talk about later in the course. But it's this Bradley Terry Luce model that's coming from behavioral economics literature. Okay. They do a bunch of other tricks to get this to work. So they use an ensemble of reward models, and they also assume there's a 10% chance that the human responds uniformly at random. Why do they do that? Yes.
Like noise, because everything is different, so then there's going to be some noise the way we were trying to case.
That is, okay, so this is a valid thing. So I'm going to talk about this in a later lecture, but this BTL model is actually incapable of capturing the fact that like you might have a different R than I do. Like it assumes we have exactly the same preferences. And that's probably not true, and we'll talk about that in a later lecture. That's actually not why they do this though. So here, by the way, in this work, this early 2017 paper, the human is rating like simulated Atari trajectories, or I don't know if it was Atari, I think it was Atari. But you know, you're watching like some agent play Atari. So it's maybe we do actually have the same preferences. It doesn't become as much of an issue. But why would there just be like this 10% chance that I pick randomly? You haven't answered in a while. Yes.
Maybe the person doesn't quite care or just mistakes with their reading.
Yeah, they don't care. They skip it. What if they just finger mush, right? What's the word for that? Like they just misclick. So here we have to think about how humans actually work when we're trying to learn from human feedback. Like their ratings aren't perfect. They just make mistakes, right? So we have to build that into the model to make it work. All right, so their results were that if you actually use raw human data, they didn't actually learn more than the game reward, like in these MuJoCo tasks, right? But if you generate synthetic preferences in that same format using the game reward, so using the true reward, that's actually even more performant in some cases than using the game reward. So showing this preference signal is a well-shaped signal that it's easy to optimize against, and validating their approach of like training the reward model and then training against the reward model. So it works really good if you have good preference data. This is in Atari. Sometimes training on human data is actually better than the game reward if you have like a very sparse reward task. But again, this preference reward can sometimes be better shaped than the game reward. So that's why it's a kind of a valid reward signal you can learn from. The cool thing about this paper was you can learn to do skills that don't have a reward function. So it's not that impressive to just like, of course, if you have the direct Atari game reward for Breakout, maybe that's going to be better. What if I want to learn something from scratch that's only in the human's brain? How can the human communicate that to me in a small number of samples? So in this case, they taught a MuJoCo leg to do a backroll just on having a human provide feedback data. So that's kind of the cool thing. All right, so then what happened is they said, okay, how do I actually train language models using human feedback? And so this actually builds on insights, the KL control stuff I was doing, and the reward model stuff that Cristiano was doing. So it's kind of bringing in those two techniques. They did, and now they're only training a language model to generate better summaries. So humans are reading the summaries. Is this a more informative or less informative summary of some text? Getting some human feedback. This was able to max some scores that they were using for summarization, but there was a lot of direct copying. And so they kind of thought this didn't actually work that well. What they did to actually improve it, how do you think you can get learning from human feedback to work better? So we got some techniques. We said the KL control, we got the reward model, we got some nice techniques. But when we trained on this human feedback, the summaries looked like a lot of copying. Why is that? What could I do to actually fix this? If you're learning from humans, it's actually really important to. So hard to get this answer in a CS class. Think about humans. Yes, exactly. So that's what they did. Our previous work reported a mismatch between the notion of quality we, the OpenAI researchers, wanted our model to learn and what the human labelers actually evaluated, leading to model-generated summaries that were high quality according to labelers, but we didn't like them. So what we did, and keep this in mind because this is how they're training ChatGPT, is paid a lot more attention to how to collect human feedback. So they did a bunch of stuff where they alternate between collecting large batches of human labels and then retraining. So this like iterative approach. But they did this very high touch approach where they screen labelers, onboard them, answer questions in a Slack. So the labelers, if they're uncertain, should ask the OpenAI researchers what is appropriate and provide regular feedback. So they're heavily training their raters to agree with them on what is good and what is bad. Because as we'll talk about later, fundamentally, this reward function can only encompass a single notion of reward. So everybody has to agree and be consistent with that to get this to work. So you have to train the labelers to basically label as the OpenAI researchers would. If you do that, so you get better researcher labeler agreement, boom, here's the big plot. So this is actually pre-InstructGPT. This is now saying, this is the model size, right? So typically we think scale is better. Bigger language model equals better. this is the first time we're seeing that a small model trained with RL post-training is generating outputs that are preferred not only to much larger models trained with supervised learning, but actually to human-generated summaries. So it's superhuman summarization. Then, there's some nuances I'm gonna have to skip over. I'll mention this. If you train on the reward model too long, performance decreases, showing that your reward model isn't perfect, but also there's some technical issues with RLHF specifically that cause this, which we can get into more later. But here's kind of their pipeline. For InstructGPT, which is our closest paper we had to describing what is ChatGPT, there's a couple of changes. In the previous paper, they actually just had people ranking which is better, like Y1 better than Y2. Now, they do two things. They have people rank a bunch. So read a bunch of outputs and say, this is better, this is better, this is better. So collecting several rankings simultaneously. Now you're getting all those pairs from that ranked list. So getting more data efficiency from the do later labelers. They do a supervised fine-tuning step. So they first have your language model trained on raw internet, then curate some instruction following data and supervised fine-tune on that. Again, that's helping the exploration work better. And they're mixing supervised updates and PPO updates. This is the whole system. And now you're also not just doing summarization, you're trying to increase alignment. So they're training to be helpful and honest and harmless, avoid bias and toxicity. What did they, in this paper, say they were going to do if these values come into conflict? If you can't be both helpful and harmless, what should you do? You would say harmless. In this paper, they said helpful. So make a better chat model rather than a completely harmless one. So this is interesting. All right, so this is the big graph again. We've actually already seen this plot, but now it's for ChatGPT style conversation, trying to be helpful, harmless, and honest. Again, the 1.5 billion parameter model trained with RL is better than models more than 100 times the size and better than human generated responses. So superhuman chatting from this. Okay, it makes models more aligned, less hallucinations. And now next week, we'll talk about what comes after this. I'm sorry we ran out of time. We're just at the last minute. If you do have questions, I'm happy to answer a couple. Or if you have to peace out, that's good too. Yeah.
So for Monday, we need to read one of the papers.
Yeah, read one of the papers on the same day as the discussion day. So it's InstructGPT, DPO, a bunch of like technical aspects of how training on the RLHF reward model for more than one epoch doesn't work, like this kind of stuff. Yes.
So in order to why is the Lagrange model supervised fine-tuning other than the error correction?
Yeah, okay, I'll draw you a good picture. So let's say this is the space of all the text humanity has ever generated. And this they have a chatbot.
One of my research projects yesterday.
If you try to do RL fine-tuning without this step, then your exploration is all possible text, and it becomes hard to search for highly rewarding instruction following. But if you first supervise fine-tuning, you move the distribution more to be in here, and then you explore within that. Maybe. Yeah. So curating this, what is your mid-training set? What is the data you use for mid-training? Is like a whole thing. And actually, there's someone in the class who works on that kind of stuff. So that's Jake. Other question is? Yeah.
already, but it seems like I was kicked out of EdSTEM.
Okay.
I had access to it like 2 days ago.
Okay. It seems